if this resistance at this interface is high enough to suppress this backflow of spins into the permalloy, the spin injection in the silver is much higher, and you get a better spin injection efficiency. Now, this is not a commercial viable process for making a device. You don't just make a device and just wait for 10 days until it has the right properties. I mean, that may work for steaks or wines or something, but not for electronic devices. But once you have figured this out, you can, of course, on purpose, put a small oxide layer at the interface to improve the properties of your device. For us, it's kind of nice because it allows us to make a device in a very simple way where we get very big signals where we then can do some physics with it. And I want to show you one example before I finish for today. Essentially, one thing that we thought, well, it's always interesting to look at temperature dependencies. They always tell you something useful, right? So what we do is we take these devices, we apply the fields so that the magnetizations are parallel to each other. We move the field, and then we measure the spin signal as a function of temperature. And this is shown here. Here's the voltage as a function of temperature. And what you see is the spin signal is kind of non-monotonic. It goes down and then goes up. And so that looks very interesting, maybe something interesting going on. Then we change the magnetization of one of the contacts, and something else happened. Well, now we have a voltage here that's negative, and then it just goes up, becomes 0, and then becomes positive at higher temperatures. And you say, whoa, what's happening here? Well, so what happens is very simple, actually. At low temperatures, we have indeed switching from a net positive to a net negative voltage, just as I explained to you in the little cartoon picture how a lateral spin valve works. At high temperatures, we get some additional voltage that gives us some offset. How does that work? Well, as you increase the temperature, the resistance of the permalloy wire and the silver wire, and also of this contact area, increases. And at the same time, we keep the current the same in the measurement. So it means as we increase the temperature, we have more and more power dissipation, especially here in this contact area. And so we heat up this contact above the nominal temperature that we have. And so we get a temperature gradient where this end is hotter than this end. And at some point we also get a temperature gradient here where the silver here is hotter than there. But this is nothing else but a thermocouple. You have two different metals in contact with each other. And so by having a temperature gradient, you get an electric voltage, a thermoelectric voltage. And this thermoelectric voltage then gives